Barium is a chemical element with symbol Bar and atomic number 56. It is the fifth element in group 2, a soft silvery metallic alkaline earth metal. Because of its high chemical reactivity, barium is never found in nature as a free element. The most common naturally occurring minerals of barium are barite and witherite, both being insoluble in water. Barium's name originates from the alchemical derivative barita, which itself comes from Greek beta alpha rho upsilon sigma, meaning heavy. Barium was identified as a new element in 1774, but not reduced to a metal until 1808 with the advent of electrolysis. Barium has only a few industrial applications. The metal has been historically used as a getter for vacuum tubes. It is a component of YBCO and electroceramics, and is added to steel and cast iron to reduce the size of carbon grains within the microstructure of the metal. Barium compounds are added to fireworks to impart a green color. Barium sulfate is used as an insoluble heavy additive to oil well drilling fluid, as well as in a purer form, as X-ray radio contrast agents for imaging the human gastrointestinal tract. Soluble barium compounds are poisonous due to release of the soluble barium ions, and therefore have been used as rodenticides. Characteristics. Physical properties. Barium is a soft, silvery white metal, with a slight golden shade when ultrapure. The silvery white color of barium metal rapidly vanishes upon oxidation in air, yielding a dark gray oxide layer. Barium has a medium specific weight and good electrical conductivity. Ultrapure barium is very hard to prepare, and therefore many properties of barium have not been accurately measured yet. At room temperature and pressure, barium has a body-centered cubic structure, with a barium-barium distance of 503 picometers, expanding with heating at a rate of approximately 1.8 times 10⁻⁵ degrees C. It is a very soft metal with a Mohs hardness of 1.25. Its melting temperature of 1000 K is intermediate between those of the lighter strontium and a heavier radium. However, its boiling point of 2170 K exceeds that of strontium. The density is again intermediate between those of strontium and radium. Chemical reactivity. Barium is chemically similar to magnesium, calcium, and strontium, being even more reactive. It always exhibits the oxidation state of +2. Reactions with chalcogens are highly exothermic. The reaction with oxygen or air occurs at room temperature, and therefore barium is stored under oil or inert gas atmosphere. Reactions with other nonmetals, such as carbon, nitrogen, phosphorus, silicon, and hydrogen, are generally exothermic and proceed upon heating. Reactions with water and alcohols are also very exothermic and release hydrogen gas. Bar plus 2 ROH bar 2 plus H2. Additionally, barium reacts with ammonia to form complexes such as bar 6. The metal is readily attacked by most acids. Sulfuric acid is a notable exception, as passivation stops the reaction by forming the insoluble barium sulfate. Barium combines with several metals, including aluminium, zinc, lead, and tin, forming intermetallic phases and alloys. Compounds. Barium salts are typically white when solid and colorless when dissolved, as barium ions provide no specific coloring. They are also denser than their strontium or calcium analogues, except for the halides. Barium hydroxide was known to alchemists who produced it by heating barium carbonate. Unlike calcium hydroxide, it absorbs very little CO2 in aqueous solutions and is therefore insensitive to atmospheric fluctuations. This property is used in calibrating pH equipment. Volatile barium compounds burn with a green to pale green flame, which is an efficient test to detect a barium compound. The color results from spectral lines at 455.4, 493.4, 553.6, and 611.1 nanometers. Organobarium compounds are a growing class of compounds. For example, D-alkyl bariums are known, as are alkyl halobariums. Isotopes. Barium occurs naturally on Earth as a mixture of 7 primordial nuclides, barium 130, 132, and 134 through 138. The corresponding half-lives should exceed the age of the universe by at least 1,000 times. Their abundance is a tilde 0.1% relative to that of natural barium. Their radioactivity is so weak that they pose no danger to life. Out of the stable isotopes, barium 138 makes up 71.7% of all barium, and the lighter the isotope, the less abundant it is. In total, barium has about 50 known isotopes, ranging in mass between 114 and 153. The most stable metastable isotope is barium 133, which has a half-life of approximately 10.51 years, and 5 more isotopes have their half-lives longer than a day. Barium also has 10 metastates, out of which barium 133M1 is the most stable, having a half-life of about 39 hours. History. Alchemists in the early Middle Ages knew about some barium minerals. Smooth pebble-like stones of mineral barite found in Bologna, Italy, were known as Bologna stones. Alchemists were attracted to them because after exposure to light they would glow for years. The phosphorescent properties of barite heated with organics were described by V. Cassiolus in 1602. Carl Scheele identified barite as containing a new element in 1774, but could not isolate barium, only barium oxide. Johann Gottlieb Gahn also isolated barium oxide 2 years later in similar studies. Oxidized barium was at first called barite, by Guyton de Morveau, a name that was changed by Antoine Lavoisier to barita. Also in the 18th century, English mineralogist William Withering noted a heavy mineral in the lead mines of Cumberland, now known to be witherite. Barium was first isolated by electrolysis of molten barium salts in 1808, by Sir Humphrey Davy in England. Davy, by analogy with calcium, named barium after barita, with the ium ending signifying a metallic element. Robert Bunsen and Augustus Matthias obtained pure barium by electrolysis of a molten mixture of barium chloride and ammonium chloride. The production of pure oxygen in the Brin process was a large-scale application of barium peroxide in the 1880s. Before it was replaced by electrolysis and fractional distillation of liquefied air in the early 1900s. In this process barium oxide reacts at 500 to 600 degrees Celsius with air to form barium peroxide, which decomposes at above 700 degrees Celsius by releasing oxygen. 2Bau plus O2 2Bau 2. In 1908, barium sulfate was first applied as a radio contrast agent in X-ray imaging of the digestive system. Occurrence and production. The abundance of barium is 0.0425% in the Earth's crust and 13 micrograms L in seawater. The main commercial source of barium is barite, which is a barium sulfate mineral. Its deposits are spread all over the world. The only other commercial source is far less important than barite. It is witherite, a barium carbonate mineral. Its main deposits are located in England, Romania, and the former USSR. The barite reserves are estimated between 0.7 and 2 billion tons. The maximum production was achieved in 1981, at 8.3 million tons, and only 7 to 8% of it was used to make barium or its compounds. The barite production has again risen since the second half of the 1990s, from 5.6 million tons in 1996 to 7.6 in 2005 and 7.8 in 2011. China accounts for more than 50% of this output, followed by India, Morocco, US, Turkey, Iran and Kazakhstan. The mined ore is washed, crushed, classified, and separated from quartz. If the quartz penetrates too deep into the ore, or the iron, zinc, or lead content is abnormally high, then froth flotation methods are applied. The product is a 98% pure barite. The purity should be no less than 95%, with a minimal content of iron and silicon dioxide. It is then reduced by carbon to barium sulfide. Besa 4 plus 2C bar plus 2CO2. The water-soluble barium sulfide is the starting point for other compounds. Dissolved bar upon reaction with oxygen gives the sulfate, with nitric acid the nitrate, with carbon dioxide the carbonate, and so on. The nitrate can be thermally decomposed to yield the oxide. Barium metal is produced by reduction with aluminium at 1100 degrees Celsius. The intermetallic compound Bal4 is produced first. 3 Bal plus 14 Al 3 Bal 4 plus Al 2O3. It is an intermediate, which reacts with barium oxide to give the metal. Note that not all barium is reduced. 8 Bal plus Bal 4 Bar plus 7 Bal 2O4. The remaining barium oxide reacts with the formed aluminium oxide. Bal plus Al 2O3 Bal 2O4, and the overall reaction is 4 Bal plus 2 Al 3 Bar plus Bal 2O4. The thus produced barium vapor is collected at the kilopart of the apparatus and then packed into molds under argon atmosphere. This method is used commercially and can yield ultra-pure barium. Commonly sold barium is about 99% pure, with main impurities being strontium and calcium and other contaminants contributing less than 0.1%. A similar reaction with silicon at 1200 degrees Celsius yields barium, a barium metasilicate. Electrolysis is not used because barium readily dissolves in molten halides and is rather impure when isolated with this method. Gemstone A barium-containing mineral benitoite occurs as a very rare blue fluorescent gemstone, and as the official state gem of California. Applications: metal and alloys. Barium, as a metal or when alloyed with aluminium, is used to remove unwanted gases from vacuum tubes, such as TV picture tubes. Barium is suitable for this purpose because of its low vapor pressure and reactivity towards oxygen, nitrogen, carbon dioxide, and water. It can even partly remove noble gases by dissolving them in the crystal lattice. This application is gradually disappearing due to the rising popularity of the tubeless LCD and plasma sets. Other uses of elemental barium are minor and include an additive to silicon that refines their structure, as well as bearing alloys. Lead-tin soldering alloys, to increase the creep resistance. Alloy with nickel for spark plugs. Additive to steel and cast iron as an inoculant. Alloys with calcium, manganese, silicon, and aluminium as high-grade steel deoxidizes. Barium sulfate and barite. Barium sulfate is important to the petroleum industry, for example, as a drilling fluid in oil and gas wells. The precipitate of the compound is used in paints and varnishes, and also as a filler in ringing ink, plastics, and rubbers. It is also a paper coating pigment. In the form of nanoparticles, it can improve physical properties of some polymers, such as epoxies. Barium sulfate has a low toxicity and relatively high density of California, 4.5 grams cm-3. For this reason it is used as a radiocontrast agent in X-ray imaging of the digestive system. Lithof-1, a pigment that contains barium sulfate and zinc sulfide, is a permanent white that has good covering power, and does not darken when exposed to sulfides. Other barium compounds. Aside from the sulfate, other compounds of barium find only niche applications. Applications are limited by the toxicity of Bar2 plus ions, which is not a problem for the insoluble Besa 4. Barium oxide is used in a coating for the electrodes of fluorescent lamps, which facilitates the release of electrons. Barium carbonate is used in glass making. Being a heavy element, barium increases the refractive index and luster of the glass. The compound is also used to reduce leaks of X-rays from cathode ray tubes, TV sets, Barium, typically as barium nitrate, is added to fireworks to impart a green color. The species responsible for the brilliant green is barium monochloride. In the absence of chlorine, a yellow or apple green is produced instead. Barium peroxide can be used as a catalyst to start an aluminothermic reaction when welding rail tracks together. It can also be used in green tracer ammunition and as a bleaching agent. Barium titanate is a promising electroceramic. Barium fluoride is used for optics in infrared applications because of its wide transparency range of 0.15–12 micrometers. YbCO was the first high-temperature superconductor that could be cooled by liquid nitrogen, as its transition temperature of 93 K exceeded the boiling point of nitrogen. Biological dangers and precautions. Because of the high reactivity of the metal, toxicological data are available only for compounds. Water-soluble barium compounds are poisonous. At low doses, barium ions act as a muscle stimulant, whereas higher doses affect the nervous system, causing cardiac irregularities, tremors, weakness, anxiety, dyspnea and paralysis. This may be due to the ability of Bar2+ to block potassium ion channels, which are critical to the proper function of the nervous system. Other target organs for water-soluble barium compounds are eyes, immune system, heart, respiratory system, and skin. They affect the body strongly, causing, for example, blindness and sensitization. Barium is not carcinogenic, and it does not bioaccumulate. However, inhaled dust containing insoluble barium compounds can accumulate in the lungs, causing a benign condition called barytosis. For comparison to the soluble poisons, the insoluble sulfate is non-toxic and is thus not classified as a dangerous good. To avoid a potentially vigorous chemical reaction, barium metal is kept under argon or mineral oils. Contact with air is dangerous, as it may cause ignition. Moisture, friction, heat, sparks, flames, shocks, static electricity, reactions with oxidizers and acids should be avoided. Everything that may make contact with barium should be grounded. Those who work with the metal should wear pre-cleaned, non-sparking shoes, flame-resistant rubber clothes, rubber gloves, apron, goggles, and a gas mask. They are not allowed to smoke in the working area and must wash themselves after handling barium.